This video looks at the impact of changing the input horizons. The previous videos have demonstrated through many examples and some argument that the use of an input horizon of 1 for most cases, and I'm emphasizing there for most cases, not all, resulted in a poorly defined optimization. If you had low output horizons, the optimization does not reflect enough of the predicted behavior to be meaningful. And if you had high output horizons, the steady state error dominates the performance index, and thus the control move goes directly to the steady state. If you've got systems with undesirable open loop dynamics, then with nu equals 1 there is insufficient flexibility within the control trajectory to form desirable predictions. And the main exception you'll notice was where the open loop dynamics were acceptable. Unsurprisingly then, what this video is going to do is look at increasing the control horizon. So we're going to look at nu greater than 1. We're going to focus mainly on nu equals 2, and then in the next video move on to nu equals 3 and 4 and so on. There still remains the possibility that you could have either a low or high output horizon. So we will look at both, though generally speaking you're probably already convinced that most of the time we should be looking at a high output horizon. What we're wanting to do really is confirm that the insights we got on the output horizon with nu equals 1 also apply when nu is larger. Now, this is a bit of a warning. There is some subtlety in what constitutes a large enough but not too large output horizon, and again that will become clearer as we go through the next few videos. The reader's reminded that we're only doing CISO examples because they illustrate the key concepts clearly, and the same principles will carry across to the MIMO case, but it would be a lot messier to make the demonstrations in the MIMO case. And aside then, we're not dealing with feed forward, we're assuming that any feed forward compensator is a constant, because there are some interactions between the feed forward and the tuning and the horizons, and therefore it's best to look at that separately. Some examples then with nu equals 2. Here's example 1, the same example as we had in the earlier videos, but now you'll notice we've allowed nu to be 2. Now this prediction isn't too bad, but I think you'd still accept that this large bit over here suggests that the overall prediction is not particularly good, it's not looking at the long term, and so any optimization based on this is not really particularly well posed. So taking nu to 2 hasn't helped enough in this case. If I increase the horizon a bit further, and here you'll see the output horizon has now gone to 10, things are looking a little bit better. With nu equals 2 and ny equals 10, I've got a prediction there that I'd be quite comfortable with. And you might argue that any optimization there is probably reasonably well posed. If I go to 20, things get even better. You can see the steady state error has almost disappeared altogether. Now here, please note, we're using a weighting of 1. So for high NY, the steady state error is small, and this means in effect that actually we've only got 1 degree of freedom. So although nu equals 2, one of your degrees of freedom has been used up to eliminate the steady state error because you have a high output horizon. Now what we've done in this one is we've decided to change lambda. Because if you look here, you'll see we've now made lambda equal to 10. And what impact has that had? You've got a hugely different steady state error, so your predictions are now much worse than they were before. And that's an interesting observation, that changing the weighting actually changes whether or not your horizons are good or poor. So the dominance of the steady state error depends upon both the weighting and the horizon. You won't get a smooth analytical link. So you'll see here, even with ny equal to 20, which on the previous slide you said the predictions were very good, now there's still quite a large steady state error. And so you cannot treat the weighting in isolation from the horizons or vice versa. In this particular case, even going up to 40, you see we've not eliminated the steady state error altogether. If we look at the open loop prediction versus the closed loop behavior, and if you remember the argument we gave was that if the predictions aren't close to the closed loop behavior that results, then your optimization is not well posed or meaningful, because in essence it means you keep changing your mind every sample. Now in this particular case, you're going to look and you're going to say, oh, ny equals 5, there is quite a big difference. The reason you normally get away with it with predictive control is that if the first move is the same, or indeed the first two moves are nearly the same, then you find the feedback tends to save you. But that doesn't mean that your optimization was well posed. It means you've had a bit of luck rather than doing a good design. If we take ny up to 20, as I've done here, what you'll notice is now the closed loop simulation and the open loop predictions are very similar. So in this case, you've got a well posed optimization. So taking nu equals to 2 seems to have been done well for this example, as long as the output horizon was big enough. Now, here we're showing ny equals 5 and nu equals 2, but what we've done is, you'll see we've made the weighting equal to 10, so we've increased the weighting, and when we've done that, you see the difference between the closed loop and the open loop is much bigger. And so how well posed is your optimization? It's not clean. You can't say, oh, this horizon's alright, that horizon's alright. You've got to look at the whole picture. Second example then. You remember this second example had a non-minimum phase characteristic. So here, if I'm using a low output horizon and nu equals 2, it's fairly clear that those predictions are poor. So this is not a good choice of horizons for this particular system. If I increase the output horizon up to 10, it's looking a little bit better, but you still look at this bit over here and it's clear that these predictions are pretty poor, and any optimization based on this is not taking account of the long term and therefore is not well posed. If I increase the horizon up to 20, it's beginning to look a little bit better, in that the error in the steady state is coming down and it's getting closer to a value that we could live with. And if you go up to an output horizon of 40, then now you've got some predictions which you're saying, well, okay, those aren't too bad, and I might be moderately confident with this choice of parameters giving me a well-posed optimization. So for this example, what we've noticed is we need an output horizon close to 40 before we have any confidence that the optimization is well posed. If we look at the open loop predictions versus the closed loop behavior, again you can see with a low output horizon there's a huge difference between the predictions and the closed loop behavior that results, which is this scenario of I keep changing my mind, and therefore the results of the optimization, if they work, it's luck rather than design. However, if I increase the horizon up to 20, you can see the difference is now much, much smaller. So now I can begin to have confidence that the result of my optimization is actually meaningful and close to a sensible result. If I increase the weighting in this particular case, it's not having a huge impact. So I've taken the weighting from 0.1, you might see that was buried there, up to 10. So a huge increase in weighting in this particular case hasn't had a big impact, and that's an interesting observation, that what changes in weight matter and what don't is problem dependent. The third example. In this example, you remember we had an unstable pole. So here, with a low output horizon, even with nu equal to 2, you're still saying, well, I'm not convinced about those predictions. Certainly the long term is very poor, so I'm slightly uncomfortable. It is better than when we used nu equals 1, but it's still not particularly good. If I take the horizon up to 10, now I'm beginning to be a bit more comfortable, because within the prediction horizon, things don't look too bad. Now, okay, everything's going haywire in the long term, but because I know this system is open loop unstable, some of that could be due to just very small residues which feedback may correct. If I go up to ny equals 20 with nu equals 2, you can see now I've got some predictions that I would be pretty comfortable with, because I know this system is unstable. I know that this tail is probably due to some quite small residues that the feedback will deal with. If I go up to 100, however, things look worse again, and you're saying, just a minute, what's going on here? I've now got this big offset. I thought as you increase the horizon, things were supposed to get better, and here they don't appear to have. Well, of course, the reason is that because this is an open-loop unstable system, your prediction matrices are made up of divergent predictions, and so as the output horizon gets large, you're going to end up with numerical ill conditioning, and that's what you're seeing here. Fourth example. This example, you'll remember, had some oscillatory modes, and in this case choosing a low output horizon really isn't good enough, and even nu equals 2 is not large enough to do anything, and those predictions are fairly poor, and an optimization based on that wouldn't be particularly useful. So here you've noticed that increasing nu to 2 is still too small to overcome and deal with the unpleasant open loop dynamics. Taking the output horizon to 10 doesn't really help. Taking it to 20 doesn't really help, because the underlying problem here is that you need more than 2 control moves in order to deal with these dynamics. So an observation summary then. Long output horizons mean that you tend to reduce the steady state error in the predictions, and what that will do is ensure that the performance index J is more representative of the real behavior, and your optimization could be considered well posed. It won't necessarily give you good behavior, but what it will help is ensure that you have consistency from one sample to the next, and therefore consistency between your predictions and the closed loop behavior that results. What we've noticed is using nu equals 2 seems to give us better predictions on average than using nu equals 1. And that's not surprising, because you've given yourself an extra degree of freedom. You're able to shape the predictions more effectively and therefore get closer to the behavior that you would really like. Now, of course, the consequence of this is you're going to struggle to justify the use of nu equals 1 in any case, unless you really have no choice. With low output horizons, we still got the same message as with nu equals 1. It was clear that the part of the prediction with J is not representative of the whole behavior, and we saw the tails beyond the horizon were often not very good, and so any optimization based on those is not particularly well thought through, because it's not looking at the long term. However, while increasing the output horizon seems to help in general, you have to be a bit careful with open loop unstable processes. It only works up to a point, and low input horizons still cause fundamental problems when the system has a difficult open loop dynamics. In other words, what we're saying is nu equals 2 is not always enough for some cases.